limit of x tends to 0, x cube cot x upon 1 minus cos x equals a 0, b 1, c 2 or d minus 2. What we do first is take the conjugate of the denominator and multiply and divide it with this term. So we get limit of x tends to 0, x cube cot x upon 1 minus cos x into 1 plus cos x upon 1 plus cos x. Now, if you solve this further, it's in the form of a minus b, a plus b. Limit of x tends to 0, x upon sin x the whole cube into limit of x tends to 0, cos x into limit of x tends to 0 and in the bracket 1 plus cos x, carry here. When you solve this term and apply the limit x tends to 0, you get the answer 2, which is option C. The value of limit x tends to 0, phi raised to x minus phi raised to minus x upon 2x equals option A log phi, B 0, C 1 and D 2 log phi. What we do first is solve the term phi raised to minus x and make it in terms of 1 upon phi raised to x, which gives us limit of x tends to 0, phi raised to x minus 1 upon phi raised to x 2x, and this would be 2x, phi raised to 2x, which gives us limit of x tends to 0, phi raised to 2x minus 1 upon 2x into 1 upon phi raised to x. This is in the term of log phi 1 upon phi raised to 0 on applying x tends to 0, which gives us log phi, which is option A. It is given that f dash of A exists, then limit of x tends to A, x f of A minus A f of x upon x minus A is equal to option A f of A minus A f dash of A, B f dash of A, C minus f dash of A and D f of A plus A f dash of A. Now, since it is given that f dash of A exists, f dash of A is equal to limit of h tends to 0, f of x minus f of A upon x minus A. Now, limit of x tends to A, x f of A minus A f of x upon x minus A equals limit of x tends to A, x f of A minus A f of A plus A f of A minus A f of x, the whole upon x minus A. Solving these terms, we get equals limit of x tends to A, f of A minus into x minus A upon x minus A minus a into limit of x tends to a, f of x minus f of a, the whole upon x minus a. Now solving this and applying the limits, we get f of a minus a into f dash of a, which is your option A. Limit of n tends to infinity, n of 2n plus 1 the whole square upon n plus 2 into n square plus 3n minus 1 equals a0, b2, c4 and d infinity. What we do first is expand this term, giving us limit of n tends to infinity, n into 2n plus 1 square. When solved, gives us 4n cubed plus 4n square plus n upon n cube plus 5n square plus 5n minus 2. On solving this equation with the numerator and denominator further, taking n cube common on both, we get limit of n tends to infinity, n cube into 4 plus 4 by n plus 1 by n square upon n cube 1 plus 5 by n plus 5 by n square minus 2 by n cube. N cube would get cancelled out, leaving us with 4 by n plus 1 by n square, and these terms with n. On applying limits where n tends to infinity, we are only left with the numerator 4, which is option C. The value of limit x tends to 0 e raised to x plus log of 1 plus x minus 1 minus x raised to minus 2 upon x square, the whole, equals a 0, b minus 3, c minus 1 or d infinity. So first, as you know, by L'Hopital's rule, we would solve this and get limit of x tends to 0 e raised to x plus log of 1 plus x becomes 1 plus x raised to minus 1 plus, and this term becomes minus 2 into 1 minus x raised to minus 3, and the denominator becomes 2x. Now further applying L'Hopital's rule on this term, we would get limit of x tends to 0 e raised to x minus 1 plus x raised to minus 2 into minus 3 1 minus x raised to minus 4 upon 2. Solving it further, now if you compare, we get limit x tends to 0 of e raised to x minus 1 plus x raised to minus 2 minus 6 1 minus x raised to minus 4, the whole upon 2. Substituting the value of x, we get e raised to 0 minus 1 minus 6 upon 2, which is minus 3, option B. For x greater than 0, limit of x tends to 0 of sin x raised to 1 by x plus 1 by x raised to sin x is A 0, B minus 1, C 1 or D 2. Applying the limits of x is equal to 0, x tends to 0, x tends to 0, sin x raised to 1 by x plus 1 by x raised to sin x. Applying the limits, we get 0 plus e raised to limit of x tends to 0 sin x log of 1 by x, and this log is natural log. Now since x tends to 0, we get e raised to 0, which is 1. Option C. Limit of x tends to 0 of x log sin x is equal to x tends is equal to option A infinity, B 0, C 1 or D cannot be determined from the information given. First, on applying L'Hopital's rule, we get limit of x tends to 0, 1 upon sin x into cos x upon minus 1 by x square. Solving this further, cos x upon sin x, limit of x tends to 0, we get cot x upon the denominator 1 by x square, which gives us limit of x tends to 0, x square comes up, and cot x, taking it down, we get tan x. We take the minus sign outside, we get minus of limit x tends to 0, 2x upon sec square x, which we get after using L'Hopital's rule again on this term and applying the limit of x tends to 0, we get 0 and sec square 0, which is 0. Option B. Limit of x tends to 0 cosec x raised to 1 by log x equals option A 1, B 0, C 1 by e, and D none of these. What we do first is define a variable p which is equal to this term, limit of x tends to 0 cosec x raised to 1 by log x. Now we take log on both sides, giving us log p is equal to limit of x tends to 0 log cosec x by log x, which on solving is limit of x tends to 0 minus of cot x upon 1 by x by L'Hopital's rule. Therefore, now we have log p equals this term. Therefore, p would give us e raised to minus 1 on applying the limits x tends to 0 on the numerator and denominator, which is 1 by e. Option C. If limit x tends to 0, k of x cos x is equal to limit of x tends to 0, x cosec kx. then the value of k is equal to option A 1, B minus 1, C plus or minus 1, D plus or minus 2. First, what we do is take the constant k outside, giving us k into limit of x tends to 0, and cosec x becomes x by sin x is equal to 1 by k limit of x tends to 0, and x cosec kx would give us kx upon sin kx. From both these equations we get k is equal to 1 by k, as these terms get cancelled out on both the sides, giving us k square is equal to 1, which leaves us with k is equal to root of 1, which is equal to plus or minus 1, which is your option C. A limit of x tends to 0 e raised to 1 by x minus 1 upon e raised to 1 by x plus 1 equals a 0, b 1, c minus 1, or d does not exist. First, what we do is, what the term is given, we write it as f of x. F of x is equal to e raised to 1 by x minus 1 upon e raised to 1 by x plus 1. Then limit of x tends to 0 of f of x is equal to limit of h tends to 0 e raised to 1 by h minus 1 upon e raised to 1 by h plus 1, which gives us limit of h tends to 0 e raised to 1 by h into 1 minus 1 by e raised to 1 by h whole upon e raised to 1 by h into 1 plus e raised to 1 upon e raised to 1 by h. These both terms getting cancelled leaves us with these two terms. On cross multiplying these, we get limit of h tends to 0 1 minus e raised to 1 by h minus 1 upon e raised to 1 by h plus 1. Applying the limits h tends to 0, we get 1, which is option B. The value of limit x tends to 0, 1 plus sin x minus cos x plus log of 1 plus x upon x cube is a minus 1, b 1 by 2, c minus 1 by 2, and d 1 by 2. So first, using L'Hopital's rule, we get limit of x tends to 0, 1 plus sin x becomes x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial and so on, minus cos becomes 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial and so on, plus x plus x square by 2 plus x cube by 3 and so on upon x cube. This whole thing is one term, which equals to limit of x tends to 0 minus x raised to 3 x cube plus all the higher powers of x. Okay, upon x cube. Applying the limit of x tends to 0, this term gets eliminated and we get 1 by 2 plus 0 on derivating these two terms, which leaves us with 1 by 2, which is option B. If f of 9 is equal to 9 and f dash of 9 is equal to 4, then limit of x tends to 9 root of f of x minus 3 upon root x minus 3 equals, these are the options, option A 2, option B minus 1, option C minus 2, and option D does not exist. On applying L'Hopital's rule on this part, we get limit of x tends to 9 1 upon 2 root f of x into f dash of x upon 1 upon 2 root x. Since x tends to 9 as the limit, we substitute x as 9, leaving us with f dash of 9 upon root of f of 9 upon 1 upon root of 9. Substituting the values of these terms as given in the question, we get 4 by 3 upon 1 by 3, which is 4 by 3 into 3, which is equal to 4. Therefore, option D. Limit of h tends to 0 root of x plus h minus root x upon h equals 1 upon 2 root x, B 1 by root x, C 2 root x, and D root x. First we apply L'Hopital's rule while we differentiate with respect to h, as the limit has h tends to 0. We get limit of h tends to 0 root of x plus h minus root x upon h. Applying L'Hopital's rule, we get limit of h tends to 0 1 upon 2 root x plus h, and applying the limits of h tends to 0, we get 1 upon 2 root x, which is option A. Limit of x tends to 0 of 2 raised to x minus 1 upon 1 plus x raised to 1 by 2 minus 1 equals option A log 2, option B log 4, option C log of root 2, and option D none of these. What we do first is we take limit of x tends to 0 and 2 raised to x minus 1. On applying L'Hopital's, we get 2 raised to x log 2 upon 1 by 2 of 1 plus x raised to minus 1, and minus 1 becomes 0. Now limit of x tends to a, f of x upon g of x gives us limit of x tends to a, f dash of x upon g dash of x. Using that principle, we get 2 log 2. Let me just write it down for you. Limit of x tends to a, f dash of x upon f of x upon g of x equals limit of x tends to a f dash of x upon g dash of x. Substituting these two terms, we get log of 2 raised to 2, which is log 4, or option B. Limit of x tends to 0, e raised to sin x minus 1 upon x equals option A 1, option B e, option C 1 by e, and option D none of these. What we do first is limit of x tends to 0, e raised to sin x minus 1 upon x. What we do first is we multiply and divide by sin x, which gives us limit of x tends to 0, e raised to sin x minus 1 upon sin x into sin x by x. Now we apply L'Hopital's rule on this, which gives us not L'Hopital's, we take the limit individually. Therefore, limit of x tends to 0, e raised to sin x minus 1 upon sin x into limit of x tends to 0, sin x by x, which gives us this is 1, and sin x by x also is 1, which is 1, and option A. The value of limit x tends to 0, 4 raised to x minus 1 the whole cube upon sin x square by 4 log of 1 plus 3x is A 4 by 3 log 4 the whole square, option B 4 by 3 log 4 the whole cube, option C 3 by 2 log 4 the whole square, and option D 3 by 2 log 4 the whole cube. What we do is we rearrange these given terms so that it is easier to solve. We therefore write limit of x tends to 0, 4 raised to x minus 1 the whole cube by x cube into x by 2 the whole square upon sin x square by 4 into 3x by log of 1 plus 3x into 4 by 3. As you can see, the numerator and the denominator both have the same powers, like cube, square, raised to 1 and raised to 0. Now it is easier to solve, as when you apply L'Hopital's and use the limit, the terms will be solved very easily. Therefore, using L'Hopital's and applying the limits, we would get 4 by 3 log of 4 cube to the base e into 1 into log of e to the base e, which would give us, this would be 1, which gives us 4 by 3 log of 4 cube by e, which is option B. Limit of x tends to infinity sin x by x equal to 1, 0, does not exist, or none of these. So we have limit of x tends to infinity sin x by x. Now let x equals to 1 by y or y equals 1 by x, so that x tends to infinity while y tends to 0, or vice versa, whichever of these you take. Therefore we get limit of, now x tends to infinity, using this substitution, sin x by x gives us limit of y tends to 0. We are writing everything in terms of y. X was substituted as 1 by y. Therefore, limit of y tends to 0 into y into sine of 1 by y, which is equal to limit of y tends to 0 y into limit of y tends to 0 and something. Now whenever you get something like this where y tends to 0 into y, you already know this term is 0. 0 into anything will obviously give you 0. Therefore we get our answer, which is B. Limit of a tends to pi by 4 sine of alpha. This is alpha tends to pi by 4 sine alpha minus cos alpha upon alpha minus pi by 4 equals a root 2, b 1 by 2, c 1 and d none of these. We now what we would want to do is get these in terms such that we can solve it easily. What we do here is we have limit of alpha tends to pi by 4. What we would do is multiply and divide both these terms by root 2, giving us root 2 sine alpha into 1 by root 2 minus cos alpha 1 by root 2. Okay. Now we can write this root 2 1 by root 2 in terms of sine and cos. And this whole divided by alpha minus pi by 4. Limit of alpha tends to pi by 4 gives us root 2 as a constant, sine alpha into cos pi by 4 minus cos alpha into sine pi by 4 upon alpha minus pi by 4. Now we have the numerator in terms of sin A cos B minus cos A sin B, which, as you know, which is equal to sine of A minus B. Taking the constant outside, we get root 2 into limit of alpha tends to pi by 4 sine of A minus B, that is alpha minus pi by 4 upon alpha minus pi by 4. Applying the limits, we would get root 2 into 1, which is root 2, option A. Limit of x tends to pi by 2 tan x into log sin x equals a 0, b 1, c minus 1 and d none of these. So we first apply L'Hopital's rule, giving us limit of x tends to pi by 2 1 by sin x cos x upon cosec square x with a minus sign. Sin cos upon sin is cot, and applying limit of x tends to pi by 2 upon cot upon minus cosec square x gives us 0, which is option A. Limit of theta tends to pi by 2 Sine theta minus tan theta equals A0, B 1 by 2, C 2 and D infinity. What we first do is we write tan in terms of sine and cos, giving us limit theta tends to pi by 2. There is a correction here. It is sec theta, not sine theta, giving us 1 by cos theta minus sine theta by cos theta. Now we merge these terms, giving us theta tends to infinity, 1 minus sine theta upon cos theta. Now we solve this further to get limit of theta tends to pi by 2 cos theta by 2 minus sine theta by 2 the whole square upon cos theta by 2 minus sine theta by 2 cos theta by 2 plus sine theta by 2. On applying the limit theta tends to pi by 2, each of these terms get cancelled out, giving us 0, which is option A. Limit of x tends to 0, x by mod x plus x square equals A1, P minus 1, C 0 and D does not exist. What we do is first write limit of x tends to 0 of f of x equals limit of h tends to 0, 0 minus h plus h square. Writing x in terms of h, we get this, which is equal to limit of h tends to 0 minus 1 upon 1 plus h, and then applying the limit h tends to 0, we get minus 1 from the numerator, and therefore limit of x tends to 0 f of x equals limit of, this is a 0 minus and 0 positive, tends to h by h plus h square. Here the signs are different because x tends to 0 negative and x tends to 0 positive, which is equal to 1. Now since we have minus 1 and 1 which are existing answers, therefore the limit for this term would not exist, which is option D. Limit of x tends to 1 tan of x square minus 1 upon x minus 1 is equal to a 2, b 1 by 2, c minus 2 and d minus 1 by 2. Now this is in the form of 0 by 0. Therefore, we get limit of x tends to 1 2x sec square x square minus 1 upon 1, taking the derivative, which gives us limit of x tends to 1 2x sec square x square minus 1. Now applying the limit, we get 2 into sec square of 0, which is 1, therefore giving us 2, which is option A. the value of limit x tends to 0 integral of 0 to x cos t square by x dt is a0, b1, c minus 1 or d none of these. What we do is first we apply L'Hopital's rule to this term, and therefore we get limit of x tends to 0 and integral of 0 to x cos t square dt by x. Therefore, limit of x tends to 0, adding the limits for the integration, we get limit of x tends to 0 cos x square, because it's from 0 to x, upon 1, which is equal to 1. Option B. Limit of x tends to 0 cos ax minus b bx upon x square equals a square minus b square by 2, b square minus a square by 2, c a square minus b square, and d b square minus a square. What we do now is substitute or replace cos ax minus cos bx in terms that we could solve easily, or that would cancel out on each other, and we could move forward with the solution. So we have the formula limit of x tends to 0 cos ax minus cos bx by x square would now be replaced by 2 sine a plus b by 2 x into sine b minus a by 2 x, the whole upon a plus b by 2 x into 2 a plus b into 2 b minus a into b minus a by 2 x. All these terms now cancel out on each other, x, and leaves us on top with a simple equation of, as you can see, this is in terms of 2 sine a sine b, which, as you know, on simplification would give you b square minus a square by 2, which is option B. We could also solve this same sum by using L'Hopital's rule, but that is a more complex calculation compared to the substitution with simple formulas. The value of limit n tends to infinity of 1 plus 2 plus 3 plus till n upon n square plus 100 is equal to a infinity, b 1 by 2, c 2, and d 0. What we do is replace the numerator with its substitution of n terms. As you know, the summation of n terms is n into n plus 1. Therefore, we get limit of n tends to infinity n into n plus 1 upon 2 into n square plus 100. N into n plus 1 by 2 is the summation of these n terms in the numerator. Therefore, we get limit of n tends to infinity n square 1 plus 1 by n upon 2 n square 1 plus 100 by n square. What we do here is take n square common on the numerator and denominator. Now, since we have these terms, they cancel out on each other, giving us 1 by 2, which is option B. Limit x tends to 0 sine of 2x plus sine 6x upon sine 5x minus sine 3x equals option A 1 by 2, option B 1 by 4, option C 2 and option D 4. What we do first is replace this in terms of sine A cos B. We do that as follows: limit of x tends to 0. Substituting this into the formula for 2 sine A cos B, we get 2 sine 4x cos 2x upon 2 sine x cos 4x, which is limit of x tends to 0, 4 upon sine 4x by 4 into x by sine x into cos of 2x by cos 4x. On substituting the limit of x tends to 0, we get this constant 4, which is option D. The value of limit n tends to infinity 1 minus n square, a summation of n will be a minus 2, b minus 1, c 2 and d 1. What we get is limit and a square minus b square, substitute as a minus b, a plus b, we get 1 minus n, 1 plus n, and summation of n would be n into n plus 1 by 2, gives you by 2. These terms get cancelled. We get 2 into 1 minus n by n. Limit n tends to infinity, which gives us limit of n tends to infinity 2 into 1 by n minus 1. Applying the limits, we get 2 into 0 minus 1, substituting n as infinity, therefore equals to 2, which is option C. If limit of 1 plus x log of 1 plus b square raised to 1 by x equals 2b sine square theta, where b is greater than 0 and summation e is ranging from minus infinity to minus pi to pi, then the value of theta is plus or minus pi by 4, plus or minus pi by 3, plus or minus pi by 6 and plus or minus pi by 2. What we do now is substitute 1 plus b square. We solve this part first, the LHS. So limit of x tends to 0, x log 1 plus b square upon x equals, taking the limits, we get 1 plus b square, which is equal to 2b sine square theta. Now we know sine square theta is equal to 1 by 2 b plus 1 1 by b. We know that b plus 1 by b has to be greater than or equal to 2. Therefore, using this, we know sine squared theta should be greater than 1, but sine squared theta should be less than 1 or equal to on both the sides. Therefore, we can assume sine squared theta is equal to 1 from both these terms. Therefore, if sine squared theta is 1, theta could possibly be either plus or minus pi by 2, which is option D. Limit of x tends to 0, sin x minus x plus x cubed by 6, the whole divided by x raised to 5 equals 1 by 120, b minus 1 by 120, c 1 by 20, or d none of these. What we do is first apply L'Hopital's rule, which will give us limit of x tends to 0, sin x minus x plus x cubed by 6, the whole divided by x raised to 5. After applying L'Hopital's rule, we get limit of cos x minus 1 plus 3x square by 6, the whole upon 5x raised to 4. Solving it further, limit of x tends to 0 minus sin x plus 6x by 6 upon 20x cube. Solving this also further, we get limit of x tends to 0 minus cos x plus 1 upon 60x square. Again applying L'Hopital's rule, we get limit x tends to 0 sin x by 120x. Now you know when we reach such a stage, we take the constant outside, limit of x tends to 0 sin x by x, which is 1 by 120, limit of x tends to 0 of cos x by 1, which is when applying the limit to cos x where x tends to 0, we get 1 by 120, which is option A. Limit of n tends to infinity for summation of 1 by n square plus 2 by n square plus 3 by n square plus till n by n square is A 1 by 2, B 0, C 1 and D infinity. First what we do is replace this whole series by its summation terms. That would be limit of n tends to infinity of 1 plus 2 plus 3 by n square, which equals limit of n tends to infinity n by 2 n plus 1 by n square. Taking 1 by 2 outside, limit of 1 by 2 into limit of n tends to infinity n plus 1 by 2, which again gives us 1 by 2 limit of n tends to infinity 1 plus 1 by n. On applying the limits, we get 1 by 2 as a constant into 1, which gives us 1 by 2, which is option A.
If x tends to a, then the value of x minus a upon x minus a is a 0, b indeterminate, c 1 or d infinite. Here, as mentioned, we know x tends to a. That means the value of x comes closer to the value of a but is never equal to a. Therefore, the value of x minus a upon x minus a would be a non-zero number. That is where the value of x minus a is not equal to 0 upon x minus a is not equal to 0. So therefore the ratio of the numbers would be same, which means on cancelling out each other it would equal to 1. Therefore answer C. Limit of x tends to 4 of x square minus x minus 12 the whole raised to 18 upon x cube minus 8x square plus 16x the whole raised to 9 equals a 2 raised to 9 by 15 raised to 18, B 5 raised to 18 upon 2 raised to 9, C 4 raised to 9 upon 7 raised to 18, or D 7 raised to 18 by 4 raised to 9. So first what we do is we write the numerator n equals x square minus x minus 12 by raised to 18, which is we can write as x minus 4 into x plus 3 the whole raised to 18. Now solving this or separating it further, we have x minus 4 raised to 18 and x plus 3 raised to 18. And the denominator d could be written as x cube minus 8x square plus 16x raised to 9, which can be separated out and written as x into x square minus 8x plus 16 the whole raised to 9. Now on separating it further, we have x into x minus 4 the whole square raised to 9, which is x raised to 9 into x minus 4 raised to 9 into 2, that is 18. Now we can take f of x, which is equal to the numerator upon denominator, and we could substitute the values as given, that is x plus 13 raised to 18 into x plus 4 x minus 4 raised to 18 upon x raised to 9 into x minus 4 raised to 18. These two terms cancel out on each other, leaving us with x plus 13 raised to 18 upon x plus 3 raised to 18 upon x raised to 9. So if we write the value of x tends to 1 by 2, then we could say 2x minus 1 tends to 0, and also 4x square minus 1 is equal to 2x minus 1 into 2x plus 1. If L is equal to limit of x tends to 1, 5x square minus 2x plus 5, and M is equal to limit of x tends to 1, x square plus x plus 2, then limit of x tends to minus 1 of x square minus L plus mx plus Lm is equal to A minus 20, B minus 45, C 20, or D 45. What we do first is solve it for L. We have 5x square minus 2x plus 5. Substituting x as 1, we get 5 raised to 5 into 1 raised to 2 minus 2 into 1 plus 5, which gives us 8. Now solving for M and substituting x as 1 in this equation, we get 1 square plus 1 plus 2, which is equal to 4. Now limit of x tends to minus 1, x square minus L plus m x plus Lm, we substitute the values of L and m respectively. Therefore we get limit of x tends to minus 1, x square minus L plus m, that is 8 minus 4 x plus Lm, that is 8 into 4, which equals, so solving this equation internally first, we get limit of x tends to minus 1, x square minus 4x plus 8 4s are 32. So therefore we have x square plus 4x plus 32. Limit of x tends to minus 1. So we have, substituting the value of x tends to minus 1, we get this is 8 plus 4, therefore we would get 12, or that would be minus 12x. Substituting the value of minus 1, we get 1 square plus 12 plus 32. That gives us 45, which is option D. If L is equal to limit of x tends to 2, x cube minus x square plus x minus 1, and M is equal to limit of x tends to minus 2, x raised to 4 minus x cube plus x square minus x, then limit of x tends to 1, lx square minus mx plus 2 upon mx square minus lx minus 2 equals A is 1, B minus 1, C minus 2, or D 2. So first we solve it for L. L is equal to limit of x tends to 2, x cube minus x square plus x minus 1. So we write L is equal to, substituting the value of x as 2, we get 2 cube minus 2 square plus 2 minus 1. Therefore we get L as 5. And for M we substitute the value of x as minus 2. Therefore we get minus 2 raised to 4 minus minus 2 cube plus minus 2 square minus of minus 2. That is 30. Now substituting the values of L and M respectively, we get lx square minus mx plus 2 as 5x square minus 30x plus 2 upon, and mx square minus lx minus 2 as 30x square minus 5x minus 2. Now taking the limits, as x tends to 1, we substitute the value of 1 with x. So therefore taking limits, we get the equation as 5 minus 30 plus 2 upon 30 minus 5 minus 2. That gives us minus 23 upon 23, which is equal to minus 1, or option B. If x tends to a by b, b by bx minus a x of bx minus a gives us a raised to n by b raised to n, then n is equals a 3, b minus 2, c 1, or d minus 1. So if L is the limit on the left hand side, then L should be equals to b by a. So we know b by a we can write as a raised to n by b raised to n, which is the right hand side. So therefore a by b raised to minus 1 equals a by b raised to n. Therefore we can say n is equal to minus 1, which is option D. Limit of x tends to 1, x raised to 18 minus 1 upon x minus 1 plus limit of x tends to 2, x square minus 4 by x minus 2 plus limit of x tends to 1, x cube minus 28 by x minus 2 equals a minus 7, b 14, c minus 7 square, or d minus 7 the whole square. So first what we do is write each term individually or solve them individually. So we have L equals, solving this term, we write x, replace x as 1. So we have 1 raised to 18 minus 1 upon x 1 minus 1. This term can be written as 18 into 1 raised to 18 minus 1. The second term, on solving x as 2. X square minus 4 by x minus 2 can be written as plus 2 plus 2. And the third term, x cube minus 28 upon x minus 2, x tends to 1, can be written as 1 cube minus 28 upon 1 minus 2. So therefore we can write it as 18 plus 4 plus, solving this we get 27. So therefore it equals 49. Or to get the answer we could put it in terms of minus 7 the whole square, which is option D. Limit of x tends to 0, cube root of 1 plus x minus cube root of 1 minus x by x equals a 2 by 3, b 1, c 1 by 3, or d does not exist. Now to solve this there are two methods. We could use the L'Hopital's rule and solve this, and on getting the form of 0 by 0 apply x tends to 0, or we could solve it as taking numerator as cube root of 1 plus x minus cube root of 1 minus x. Now we could write this as 1 plus x raised to 1 by 3 minus 1 minus x raised to 1 by 3. So this on expanding can be written as 1 plus 1 by 3 x minus 1 minus 1 by 3 x. Now substituting the values or solving the equation and expanding both these terms, we could write it as 1 plus 1 by 3x minus 1 plus 1 by 3x. These two terms gets cancelled and we are left with 2 by 3x, which gives us the answer A. If x tends to 0, tan px by sin 3x is equal to 4, then the value of p equals a4, b6, c9, or d12. So we could write tan px by sin 3x as in the terms of px by 3x, which is equals 4 as given in the question. So to solve for the value of p, we just need to cross multiply. We get px is equal to 12x. So from this we can write p is equal to 12, which is option D. Limit of x tends to 0, sin cube bx by x sin square ax equals a minus b cube by a square, a square by b cube, c b cube by a square, or d minus a square by b cube. So we can write this as sin cube bx upon x sin square ax can be written as bx the whole cube upon x into ax the whole square, since the limit limit x tends to 0. Therefore we get b cube x cube upon a square x cube. X cube gets cancelled, we are left with b cube by a square, which is option C. Limit of x tends to 0, a sin ax minus b sin bx upon tan ax minus tan bx equals option A plus b, b a minus b, c b minus a, or d a square minus b square. So what we do is, to solve this we have to divide the numerator and divider by x. So we could write f of x is equal to a into sin ax by x minus b sin bx by x upon tan ax by x minus tan bx by x. Now we could apply the limits for x tends to 0, which leaves us with a into a minus b into b upon a minus b, which is a square minus b square upon a minus b. Expanding these terms, we get a plus b into a minus b upon a minus b. These terms get cancelled out. We are left with a plus b, which is option A. Limit of x tends to 0 sin px by tan qx plus tan mx by sin nx plus cot bx by cot ax equals option A p by q plus m by n minus a by b, b p by q plus m by n plus a by b, c p by q plus n by m plus b by a, or d p by q plus m by n minus a by b. So first what we know is we could write cot of bx by cot of ax equals tan of ax by tan bx. So we could write this as a function f of x, which is px by qx for this term, plus mx by nx for this term, and bx by ax for the third term. X cancels out on all, leaving us with p by q plus m by n plus b by a, which is option D, which is option B. Sorry, it's option C. B by A. Limit of x tends to pi by 2 sine of x by x equals a 1 b 1 degrees, c pi by 2, or d 2 by pi. So we know limit of x tends to pi by 2 sine x by x is given. We could replace x by pi by 2 on substituting the limit. That leaves us with sine of pi by 2 upon pi by 2, which leaves us with 1 upon pi by 2, which gives us 2 by 5, which is option D. Limit of x tends to 0 sin x square by x equals a0 b1 cx or d pi. What we do first is apply the limits that gives us sin x square by x, which gives us sin x square by x into x, sin x square by x. So this could be written as sin x by x into x. This would be sin x square. So on applying the limits, we know this would be equal to 0. 0 into anything would give us 0, which is option A. Limit of x tends to 0 sin x by x square equals a 0 b 1 c 1 by x, or d does not exist. So we could write this as sin of x by x square. Take the term as in the form limit of x tends to 0 sin x by x into 1 by x, which gives us, applying the limits, we get this term as 0. So therefore 1 by 0 would be infinity. Therefore D. Limit of h tends to 0 sin square h by 2 by h square equals a 1 by 2 b 2 c 1 by 4 or d 4. So we could write this as sin square h by 2 by h square in the terms of h by 2 the whole square by h square on applying the limit of h tends to 0. So therefore we get h square by 4 by h square. That leaves us with 1 by 4. That is option C. Limit of x tends to 0, sine of x square minus 3x upon x equals a1, b x minus 3, c minus 3, or d 0. So we could write sine x square minus 3x by x after applying limits as x square minus 3x by x. Substituting the expanding the numerator, we get x minus 3. On substituting the value of x as 0, we get 0 minus 3. Therefore, we are left with minus 3, which is option C. Limit of x tends to 0, 1 minus cos cube x by x sin x cos x equals a 2 by 5, b 3 by 5, c 3 by 2, or d 3 by 4. What we do first is we solve the numerator and numerator and denominator individually. So we get 1 minus cos x upon x square into x by sin x into 1 plus cos x plus cos square x upon cos x. Now we get this term on separating the numerator and divider. So we get, on applying the limit of x tends to 0, it is easier to solve each term. We get 1 by 2 into 1 plus 1 plus 1 the whole square upon 1. That gives us 3 by 2, which is option. Limit of x tends to 0, 1 plus 2 by x 1 minus cos x by x equals a0, b4, c1, and d minus 1. So therefore what we do is separate out these terms and apply the limits on them individually. That gives us for each term we get x plus 2 into, multiply x on the other side, that gives us 1 minus cos x by x square equals, that gives us, on applying limit, we would get 0 plus 2 into 1 minus cos x by x square would give us 1 by 2. So 1 by 2 into 2 gives us 1, which is option C. Limit of x tends to 0, cosec x minus cot x equals a0, b minus 1, c1, or d2. Now to solve this, we'll represent it in terms of sine and cos. So therefore we get 1 by sine x minus cos x by sine x. Now applying limits, we would get 1 minus cos x upon sine x into 1 plus cos x upon 1 plus cos x. That gives us sine x upon 1 plus cos x, which equals, now applying x tends to 0, we get 0 by 1 plus 1, which is 0. That is option A. Limit of x tends to 0, sin x minus tan x upon cos x minus sec x equals a minus 1, b 0, c 1 by 2, or d 1. For this we write, we need to change the terms in terms of sine and cos only. So therefore we get sine x into 1 minus 1 by cos x, and cos x minus 1 by cos x. So therefore we get sine x cos x minus 1 upon cos square x minus 1. Now cos square x can be written as it is, and sin x, that is sin x into cos x minus 1 gives us only sin x upon cos x plus 1 on cancelling out on each other. Now applying the limits of x tends to 0 and substituting the values in this term, we get 0 upon 1 plus 1, which again is 0. That is option B. Limit of x tends to 0, 1 minus cos mx upon x into sin nx equals a m square by n, b n by m square, c m square by 2n, and d minus n square by 2m. So what we do first is we write the equation in terms of 1 minus cos mx upon x into sin nx. That gives us 1 minus cos mx, and take x out, giving us nx. Now take 1 by n outside, therefore we get 1 by n into, this is an n, into 1 minus cos mx upon x square. Now we can use the limit of x tends to 0. That would give us 1 by n into m square by 2. That is m square by 2n, which is option C. Limit of x tends to 0, cos ax minus cos bx upon x into sin cx equals a square minus b square by 2c, b minus a square minus b square by 2c, c a square plus b square upon 2c, or d a square plus b square by minus of a square plus b square by 2c. So therefore we could write this equation as cos of ax minus cos bx upon x sin cx. This could be written as 1 minus cos bx minus 1 minus cos ax upon x cx. That gives us, taking 1 by c constant outside, we get 1 by c 1 minus cos bx by x square minus 1 minus cos a x by x square. Now that gives us 1 by c, on applying limits of x tends to 0, b square by 2 minus a square by 2. We could take 2 common and adjust the term minus to get minus of a square plus b square upon 2c, which is option D. There's a mistake here. Limit of x tends to pi by 4, 1 plus sin 2x upon 1 minus cos 4x equals a minus 1, b 0, c 1, or d infinity. What we need to do first is we could substitute the value of, or apply the limits x tends to pi by 4, substituting the value of x as pi by 4. That gives us 1 plus sin 2 into pi by 4 upon 1 minus cos 4 of pi by 4.
Now solving this, we get 1 plus sine pi by 2 upon 1 minus cos pi. Substituting the values for sine and cos pi by 2 and pi respectively, we get 1 plus 1 upon 1 minus of minus 1, that is 2 by 2, which gives us 1, which is option C. Limit of x tends to pi by 2 sec x minus tan x equals a minus 1, b 1, c 0 or d 2. So sec x minus tan x can be written as 1 by cos x minus sin x by cos x. Now we could write these terms as 1 minus sin x upon cos x into 1 plus sin x upon 1 plus sin x. That gives us cos x upon 1 plus sin x. On applying the limits of x tends to pi by 2, we replace the values of x as pi by 2. And solve using the values of cos pi by 2, which is 0, we get option C as the answer. Limit of x tends to 0 root of 1 minus cos x square upon 1 minus cos x, which is equal a 1, b root 2, c root 3 or d 2. So we could write the term 1 minus cos x square the whole root upon 1 minus cos x as root of 1 minus cos x square by x raised to 4 into 1 upon 1 minus cos x by x square. Now applying the limits of x tends to 0 on this term, we get root of 1 by 2 into 1 upon 1 by 2, which gives us 2 by root 2. Now multiplying and dividing this by root 2, we get root 2, which is option B. Limit of x tends to 0 tan x minus sin x upon x cube equals a1, b 1 by 2, c minus 1 by 2 or d minus 1. To solve this, what we do first is write this term in terms of sine and cos only. So we have sin x by cos x minus sin x of the whole upon x cube, which gives us sin x 1 by cos x minus 1 by x cube. Now we have sin x by x into 1 minus cos x by x square into 1 by cos x. On applying the limits of x tends to 0, we get 1 into 1 by 2 into 1, which gives us 1 by 2, which is option B. Limit of x tends to 0, 1 minus x the whole raised to 1 by x. So we could write, and the options are A 1, B 0, C E and D 1 by E. We could write this term as 1 minus x the whole raised to 1 by minus x the whole raised to minus 1. Now this, on applying limit x tends to 0, gives us e raised to minus 1, and e raised to minus 1 is nothing but 1 by e, which is option T. Limit of x tends to 0, 1 plus mx by 1 minus mx the whole raised to 1 by x equals a 2e raised to m, b e raised to m square, c e raised to 2m or d 2em. So this could be written in the terms of 1 plus mx as 1 plus mx upon 1 minus mx. Numerator raised to 1 by x and denominator also raised to 1 by x.
On applying the limit of x tends to 0, we get this as e raised to m and e raised to minus m. Taking this on top, we get e raised to m into e raised to m, which is e raised to 2m, which is option C. Limit of x tends to 0, a plus x, a minus x, the raised to 1 minus x equals a 2 by e raised to a, b 2e a raised to a, c 2e raised to 1 by a, or d e raised to 2 by a. We could write this term as a plus x by a upon a minus x by a, the whole raised to 1 by x. Now solving this, we get 1 plus x by a upon 1 minus x by a, the whole raised to 1 by x. On applying and solving it further, we have 1 plus x by a upon 1 minus x by a, the whole raised to 1 by x. Now what we do is take it individually. So we'll have the numerator raised to 1 by x and denominator raised to 1 by x. On applying the limits for these terms, we get e raised to 1 by a and denominator as e raised to minus 1 by a. So therefore it is e raised to 2 by a, which is option D. Limit of x tends to 0, a plus bx upon a plus cx, the whole raised to 1 by x equals a e raised to b minus c, b e raised to 2a, c e raised to b plus c by a, or d b e raised to b minus c by a. What we do is write this term in terms of 1 plus b by a x upon 1 plus c by a x, the whole raised to 1 by x. Taking 1 by x for the numerator and denominator individually, we get numerator raised to 1 by x and the denominator raised to 1 by x. Now this gives us e raised to b by a upon e raised to c by a. Taking it on top, we get e raised to b minus c, the whole by a, which is option D.